Hello, here's a couple more thermodynamics related questions. So we're starting here with figure 6.1 shows the apparatus used to observe Brownian motion using pollen grains suspended in a liquid. So that is the original and classic Brownian motion experiment. State two conclusions that may be deduced about the molecules of the liquid from the motion of the pollen grains observed in the microscope. Right, so if you remember with this, the pollen grains they're jiggling around in this very sort of rapid jiggle, random motion that's going on, and that is telling us two things, well, two main things about the molecules in the liquid. So that is the liquid molecules are much smaller than the pollen grains. They're much smaller than the pollen grains, so that's why we're getting that rapid jiggling effect, and then also that the liquid molecules have got random motion, and that is what's creating the random path of the pollen grains. So those two main things. So that's that first bit. Suggest how the motion of these pollen grains could be increased. Well, if we're going to increase the motion of the pollen grains, we need them to be getting hit harder by the liquid molecule. So we need more energy in the liquid. So we need to raise the temperature of the liquid. That will mean that we've got more energy to impart onto the pollen grains. Right, part B. State three assumptions made in the development of the kinetic model of an ideal gas. Right, we've got 5 or 6 that we could put down. So I'm just going to say the ones that come into my head. I'm not going to write them all down. Well, you've got the 3 negligible ones, haven't you? You've got the force between molecules is negligible except during collisions. The volume of the molecules is negligible compared to the volume of the gas. And the time of collisions, either between molecules or with the container of the gas, is negligible compared to the time between the collisions. So they're the 3 negligible ones. Then there's what we got. There's the gas itself is a very large number of molecules moving with random speeds and directions. And what's the 5th one? I always go for. I'm trying to remember now. Oh, the elastic collisions. All collisions between molecules and with the container of the gas are elastic. So any 3 of those will do. Right. Use the kinetic model of a gas and Newton's laws of motion to explain how the gas exerts a pressure on the walls of the container. Right, so you really want to be making proper statements here where you're mentioning the Newton's laws. So I'll write out a chain on these, and I didn't write out anything for the last one. So we want to say something that, so the molecule collides with the wall, So that leads to a momentum change. Obviously, write these in sentences rather than just symbols. So you've got a momentum change. Therefore, we've got the force on the molecule from the wall is equal to the rate of change of the momentum. And then you can say there that's Newton's second law, because we certainly want to mention which Newton's laws we're using. Then we can say, therefore the force on the wall from the molecule, so flipping it around in our usual Newton's third law way of just changing the order of the words in the sentence, is the force on the wall from the molecule is equal magnitude and opposite direction. And then we can say that's Newton's third law. And then we need to, what do we end up here? Well, we want to get to explaining the pressure bit. So we just have to say at the end now, the pressure is the sum of the forces divided by the area of the wall. So by the time you've put that into full sentences, you've got a nice chain then all the way through, explicitly bringing in Newton's second and third law and ending up with the pressure at the bottom. So that was a nice one. You get quite a lot of marks for this section here, I would have thought, writing all that out. Part C, the ideal gas equation PV equals nRT show that the pressure P exerted by a fixed mass of gas is given by that equation, where ρ is the density of the gas and m is the mass of 1 mole of a gas. Okay, right, so on this then, so let's write out, we clearly want to get in these 2 things here. So let's say what they are. So density is equal to little m mass over volume, and big M mass, so this is the mass of 1 mole. So that will be equal to, that's going to be the little m, the total mass we've got, divided by the number of moles, if we're looking for mass per mole. So now we just have to stick all of this in and replace what we're getting rid of. We're getting rid of N and we're getting rid of V. So this means, so we can say P is equal to N RT over V, which is there, well, N we're saying is little m over big M times R times T, and then 1 over V is rho over little m. And then the little m's are going to cancel, and we're going to get rho RT over big M. Right, so I should have been clear. So that is big M, to be clearer on these. That is big M. It's the trouble with M's, they all look the same, particularly when I'm writing too quickly on here. So that was easy enough. So that's rounded off that question. We got up next. Oh, we got part D. Okay, so we haven't finished off that question. We got another part of the question. The Earth's atmosphere may be treated as an ideal gas whose density, pressure, and temperature all decrease with height. In 1924, these people climbed up Mount Everest. They got to that height above sea level. Right, so air pressure is 0.3 times the pressure at sea level. That's the temperature, compared to what we've got there for the temperature and density at sea level. Okay, so let's see what they're asking. We might have to go back into all those sentences. Calculate the density of the air at a height of that at the time it was set. Right, so we just worked out on the previous part that P was equal to rho RT over capital M. So if we do, and we want to get what? We want to get density. So we're saying that density is P times M over R times T. So if we do a ratio of these things, we can do rho, we want to get the altitude one. So let's go to rho at altitude divided by rho at sea level is going to be, well, the M's and the R's are going to cancel because they're going to be constant. I mean, R is a constant, and capital M is the mass per mole. So that isn't changing. So we're going to end up with P altitude multiplied by T sea level divided by P sea level multiplied by T altitude. So we just need to stick all of these things in. So what was it? Oh, it was, oh, we got a ratio of the pressures already, haven't we? So that's 0.35 multiplied by 20 degrees C. So we've got to say 293 to get it into Kelvin. Divide by, so minus 33 is 240 Kelvin. So the density at altitude is going to be, what was the density at sea? 1.3 times 0.35 times 293 divided by 240, which is equal to, putting it all in the calculator, 0.555479, so 0.56 kilograms per meter cubed. Right. Determine the ratio of the number of air molecules present in Somerville's lungs at the top of his climb, number of air molecules present in Somerville's lungs at sea level. You can assume that the volume remains the same, right? If the volume remains the same, then, because we've got density is mass over volume, and the number of molecules is going to be proportional to the mass, which is going to be then proportional to the density. So we just need to come back to the ratios of the densities on this, which is this bit. So it's that divided by the 1.3 that we put on there. That's all we're going to end up with. So divide that by 1.3 and we get, what do we get? So 1.3 leaves us to 0.42729, so 0.43. Right, that was, yeah, they could have done that the other way round, seeing as we worked out that ratio first and then multiplied by the 1.3, but hey ho. Right, that must be the end of that question. So that's that one sorted. Let's move on to, what is this? Yes, we've got a new question. This will be the last bit that I do in this. It seems to be the end of a block. The room measures that the air in the room is heated by a gas-powered heater from 12 to 21 degrees C. That's density of air. It's assumed to remain constant. Calculate the thermal energy required to raise the temperature of the air in the room. There's the specific heat capacity, right? So we need mc delta T. So we need the mass of the air, which is going to be 4.5 times 4 times 2.4. So that's the volume, multiplied by the density, which is the 1.3, multiplied by 990, which is our specific heat capacity, multiplied by 9, which is our temperature rise. So that comes out at 500,385.6, so 500 kilojoules. Okay, the heater has an power output of that 2.3 kilowatts. The heating gas has a density of that. Each cubic meter of heating gas provides that amount of energy. Use your answer to A to calculate the time required to raise the temperature. So we're getting 2.3 kilowatts and we need to get up to 500 kilojoules. So the time is going to be equal to 500. We can ignore the kilos then and just divide by 2.3, which gives 217.56 seconds. So 217.6. So 200, and we're doing two significant figures by the look of it. So 220 seconds. Then we need the mass of the heating gas used in that time. Right, so what have they told us? Right, we're getting that amount of energy per cubic meter. So we need to do, so the volume of gas, and then we need to multiply it by the density. So the mass is equal to the volume times the density, and the volume is going to be, well, it's what do we have, 500 kilojoules. So 500, well, let's put that in megajoules, and then we don't have to, so 0.5, that's in megajoules, and then just divide by the 39. That gives us the volume of gas multiplied by the density, 0.72, and that leaves us with a small number. That is 9.238, so 9.2 times 10 to the minus 3 kilograms. Okay, so that's part B done. Suggest 2 reasons why the time required and the mass of heating gas will in practice be greater than the values carried out in calculated in B. Right, these are the ones, so they want 2 specific reasons. Now, obviously, everything here is going to be to do with losses and inefficiencies, but you can't just say, oh yeah, there's losses, oh, heat lost the surroundings. They want you to be specific, particularly as they've asked for 2 reasons here. So let's say for one, we could say you've got to heat other objects in the room, because we're heating the air in the room. The room doesn't exist in isolation. So let's say heat other objects in the room. I mean, you could say you've even got heating the walls or the floors of the room. You could have that as an alternative on that one. You could say then that we've got air loss, so we could have, that could be hot air going out, hot air leaving room, or cold air coming in, or cold air entering. So it's still, obviously all these fall under the category of losses and inefficiencies, but you're being more specific rather than just doing this, oh well, I don't know, it's a loss, isn't it? You're actually saying, let's contextualize this, let's talk about the other objects that might be in the room, the walls of the room, any air losses that might be happening here, or air changes that might be going on. So be as specific as you can, even if it seems obvious, because that's how you end up picking up the marks. Right, so I'll leave those ones there because that's finished this little block.